Hi everyone, welcome back. So we're continuing our discussion about differentiating different types of functions. We've got the product rule, the quotient rule, derivatives of trig functions. So we know how to do derivatives of a lot of functions, and this section is going to be about the chain rule, which is another big rule to help us do lots of derivatives. So let's go ahead and get started. So before I show you the chain rule, I want to show you what type of problem we need a new rule for. Like, what type of problem can we not do yet? And an example, I'm going to pose this as a question, but I don't expect you to answer it right now. Given y equals sine of x squared plus 1, what is y prime? So let's think about this. Even if I'm saying that we aren't ready to solve this just yet, let's think about this and see why we need a new rule. Like, why do we need to add another derivative rule? We already know how to do the derivative of sine. But when we talked about the derivative of sine, it was just the derivative of sine x. This is the derivative of sine of some other stuff. By the way, I know how to do the derivative of x squared plus 1. So the thing that's in parentheses, we know the derivative of that. We know how to do the derivative of sine x, but this is not a product. It's not sine times this stuff. It's sine of this stuff. So let's talk about it. Note, I'm going to say we know how to differentiate, how to find derivatives of sine x and x squared plus 1, but not when they're together like this. Not when it's sine of something more than just x. So I'll show you what we're going to do. There's a trick that we're going to do. We're going to introduce another letter. We're going to say f of u is sine of u. And g of x, I guess we're introducing two extra letters. G of x is x squared plus 1. So if I introduce a function called f of u, and I let it be sine of u, and I introduce g of x, and I let it be x squared plus 1, I'm letting g of x be the sort of inner function, the part that's in parentheses. And I'm letting f of u be the sort of outer function, the thing that's on the outside of the parentheses. If I do that, then the function y that we were given up above is equal to f of g of x. I set up f and I set up g so that the function we're interested in is f of g of x, sine of x squared plus 1. And we have a name for this type of function, right? You've seen this type of function before in pre-calculus or in algebra. This is a composite function. Do you remember in those classes when you talked about f of g, or sometimes it might be called f composed with g? A function of a function. That's what we need to learn how to take derivatives of. How do we take derivatives of a composite function? Now, we've already seen rules for sums of functions, differences of functions, products, quotients, and now we're going to establish a rule for doing derivatives of composite functions. Now, we could call this the composite rule or the composite derivative rule or something like that, but instead we call it the chain rule. And I'm just going to state what the rule is first, and then we'll see some examples with it. First of all, if g is differentiable. Oh, by the way, uh, let's just take a moment here and think about those other rules that we know, like the product rule and the quotient rule. They're basically formulas, right? So what we're hoping is that the chain rule, we're hoping it's going to be some formula, and maybe it's going to involve f and g and give us some kind of formula for finding the derivative. And it will be a formula, but it'll be a formula at the end of a very long sentence. If g is differentiable at x and f is differentiable at g of x, then the composite function h equals f composed with g. Do you remember that notation from like algebra classes, the little circle? F composed with g, defined by h of x equals f of g of x is differentiable at x, and the derivative is. All right, that's the long sentence. Now we can say the formula for the chain rule. What do we want the derivative of? So we introduced these extra letters. Really what we want to find is the derivative of this composite function. So we want the derivative of h. So we want a formula for h prime. That's really what we want. Now, you might be thinking, you know, wouldn't it be nice if it's just like f, if we just put prime on f and prime on g, like f prime of g prime? Unfortunately, that's not the rule. It's not that simple. What we need to do is f prime of g of x times g prime of x. And that is the entire rule. That's the formula. I'll give you a chance to see that. Notice where the prime symbols are. Now, I think when we did the product rule and the quotient rule, I showed you them written in a few different forms, but I think for the chain rule, it's best to just keep it in this form instead of trying to do like ddx or anything like that. I like this form, the prime notation. Now, just like with the product rule and quotient rule, you know, we don't have to label the functions as f and g. We might just think of them as the first function and the second function, or we might think of them as sort of the outer function and the inner function. So later, if we have a problem where we're given a function called f, we could still work with it. We'll just think of the two pieces. The chain rule, the way that it's phrased here, this could actually be called a theorem, because it actually tells us that the composite function is differentiable and it has this formula. Now, with the product rule and the quotient rule, we derived those rules, so we basically proved why they worked. This time, I just told you the rule and I haven't proved it for you. And I think what I'm going to say is we will discuss deriving this later if we have time. However, I will also say that a full proof of this, like 100% proof of this, can't really be done yet at this point in the course. In the textbook that I'm following along with, it's actually done a few sections later, a proof of the chain rule. So maybe we'll revisit this at that point in time. For now, we'll do some examples and we'll see what kinds of problems we use this on. And I want to tell you that even though the chain rule is a formula, I often think of it more as like a technique or a strategy. So example problems are going to help a lot. for the first example, let's do the function that we wrote above that I said this is why we needed a new rule. Let's try to find y prime. And I'm going to solve this by introducing f of u, like we did above, and g of x, like we did above, where I'm kind of figuring out, for this problem, what is the outer function and what is the inner function. The innermost thing, I mean by order of operations, the thing in the parentheses, the x squared plus 1 would be on the inside. That's what we're going to let be g of x. And then the stuff on the outside, the sign, is going to be f. So in order to use the chain rule formula, we need to know the derivative of f and the derivative of g. So let's write them underneath. F prime of u, let's set it up like this, and g prime of x. We're going to need both of those before we use the formula. So these are like two small derivative problems within, like two problems within the problem. Luckily, these ones are small derivatives, like the derivative of sine is cosine. So we could say cosine of u. We kind of just took the derivative with respect to u, because that's what the variable was here. And then over here, the derivative of this is 2x. So let's use the chain rule formula. So I'll say, now we have all of the pieces that we need. Chain rule formula says y prime is supposed to be f prime of g of x times g prime of x. So what does that look like for this problem? Well, f prime, we said, was cosine. F prime of u is cosine of u. So right here, I'm going to write cosine. Cosine of. But instead of cosine of u, this formula wants us to do f prime of g. So cosine of g of x. So g of x is x squared plus 1. So let's put that here. And then times g prime of x. What did we find for g prime of x? We found 2x. And we did it. We found y prime. I think the only thing I'm going to do is one more step to rewrite this problem, to rewrite the answer in a different way. I don't really like having the 2x all the way here to the right. I think it would look nicer if we moved the 2x out front, and then we'll just put a box around it. There we go. That's the answer. All right, so as you're doing these, what I would suggest is look at these problems and think of what is the inner function and what is the outer function, and identify them and label the inner function as g and the outer function as f. Remember, with the product rule, we also had to first identify the two parts, and the same with the quotient rule, same with this. We have to identify the two parts, and then we can work on it. Now, I said that the chain rule I think of often as more of a strategy, so let me talk a little bit about that. What you do is you let f of u be the outer function. Outer with respect to the order of operations, it's kind of the thing on the outside, the thing that would be done last, or the thing that would be done second. And let g of x be the inner function, the thing that according to order of operations would be done first. And this is something that's in parentheses, under a square root, in an exponent, etc. Okay? In the problem that we just did, the inner function was inside parentheses, so it was easy to identify that it was on the inside. But I'm saying that it could also be like on the inside of a square root symbol. Or it could be up in an exponent. Or we'll see if anything else comes up. So let me show you some other problems. I think we're going to try to do a lot of example problems for the chain rule. Because the more you see, the more you'll get used to this as a strategy. So, example, I'll do this one for us. Let's say we're given capital F of x equals the square root of x squared plus 1. And we want to find capital F prime. And, you know, believe it or not, this is something that we would not be able to do before this lesson. You know, even though we know how to do derivatives of x squared plus 1, and we know the derivative of square root, when they're put together like this, we need the chain rule. So I'm going to set up the same kind of strategy that I did on the previous problem. I'm going to say we need f of u. How about this? How about this? We need 4 things. I'm going to set up room for all 4 pieces. Aren't these the 4 pieces that we need? So you could kind of do this as like a template for chain rule problems. Once you've identified that it's a chain rule problem, you could say, I'm going to need these 4 things in order to use the chain rule formula. All right, so think of setting it up like that. And then you have to identify the inner and outer function. Well, I've already said that the inner function is something that could be under a square root. Sometimes the inner function is easier to identify first. So anyway, I think the inner function is x squared plus 1. It's on the inside of a square root. Now let's say, what is f of u? Well, it would have to be the square root, right? The thing on the outside is the actual taking of the square root. So let's call it the square root of u. We choose these so that if you did f of g of x, it would equal the original problem. F of g of x would equal the original problem. That's how you know you set it up correctly. What are the derivatives of these? You could, well, this is the easy one. This is 2x. Derivative of that is 2x, right? What's the derivative of the square root of u? Well, u is the variable here. We've done the derivative of the square root of x before. Now it's just labeled u. It's a couple of ways to write this. Here, scratch work. I shouldn't have to spend much time on this kind of thing, but we're doing the derivative with respect to u, so maybe I'll call it d du of the square root of u. So think of it as u to the 1/2. The 1/2 comes down out front, u to the negative 1/2, right? Isn't there another way we could write that? Instead of u to the negative 1/2, I could say 1/2 square root of u. That was all scratch work. That was all to figure out that what goes here is 1/2 square root of u. Okay, now we're ready to use the chain rule formula. In this case, the original problem was called capital F, so I'll write capital F. We need f prime of g of x times g prime of x. And in this case, let's put all the pieces together. First thing that we see is f prime. F prime is 1/2 square root of something. So it's 1/2 square root of... We want f prime of g of x. So instead of f prime of u, we want f prime of g of x. So here's g of x. X squared plus 1 is what we're putting in here. times g prime. So we did it. We found the derivative. Anything else that we do is just going to be some simplifying steps. And I think the simplifying step I see is that we have a 2 over 2. So let's cancel the 2's and let's leave the x up top. And this is going to be the answer. There we go. And you can't really simplify it any more than that. So I think this sort of strategy of setting up a spot for f of u, g of x, f prime of u, g prime of x, finding the 4 things that you need and then putting them into the chain rule formula. That's why I tend to think of it as more than just a formula. It's more like a strategy. I have a problem I'd like you to try. So I'm going to ask you to differentiate y equals parentheses 4x minus x squared, close the parentheses, raised to the 100. Okay, so take a minute and give this a try. You could pause the video. All right, so this is another one for the chain rule. I guess technically you could say, isn't this technically a polynomial? I feel like technically we could expand this out. It's raised to the 100, so you imagine 100 copies of this thing. 4x minus x squared times itself, times itself, times itself. Technically, it could be all expanded out. You'd have a gigantic polynomial, but it would take forever to do that. So in this case, the chain rule is providing kind of a quicker way to differentiate it. Some of the other problems, we didn't have any choice. We had to use the chain rule. For this one, it's just a really great shortcut. Look what I'm doing. Setting up room for the 4 pieces that I know. These are the 4 pieces of the puzzle. Okay, I think, again, the thing that's on the inside, the inner function, is in parentheses 4x minus x squared. And then the thing that's on the outside is the raising to the 100. Something is being raised to the 100, so we'll call it u to the 100. Now we need the derivatives of these two things. The derivative of u to the 100 is going to be 100u to the 99. And the derivative of this thing here is 4 minus 2x. So let's do the chain rule formula. Y prime is f prime of g of x times g prime of x. Notice that as we do these, the chain rule formula is telling us to do f prime of the inner function times the derivative of the inner function. So there's always this times g prime on the outside. So all of these ones that we're doing, it's kind of like this 2x that we had in the previous problem. Like, where did that 2x come from? It was the derivative of the inner function. So anyway, what's f prime? F prime is 100 something to the 99. In this case, it's 100 this to the 99. And then we need times g prime. Right? I still need to write something here. G prime is 4 minus 2x. Is it okay for me to write 4 minus 2x here? If I just write 4 minus 2x? Well, if you think about it, I need parentheses. I need to add parentheses. Even though we didn't have the parentheses around it here, we need it. We need parentheses here. So this right here is a good answer. I would just leave it like this. You could move some things around if you want, but I think it looks fine the way it is. As long as you have these, you need these. Why do I need those? You might look at it and say, well, 4 minus 2x was written as 4 minus 2x here. Why can't I just copy it down here? If you don't put these parentheses here, then what you're writing means something else. If you don't put the parentheses, what you are saying is take this times 4 and then subtract 2x. We don't want to do this times 4. We want to do this times 4 minus 2x. 4 minus 2x needs to stay together as one object, and the way we do that in math is with parentheses. So sometimes you might need to add parentheses to make sure something is treated as one object. In this case, 4 minus 2x. All right, so watch out for that in problems. Okay, so a little more that we have to talk about. We will see some more example problems, but I want to take a step back and talk about something else before we do that. I want to talk about exponential functions. You know how we had a lesson on derivatives of exponential functions? And that lesson mostly focused on e to the x. We found the derivative rule for e to the x, okay? And then at the end of that lesson, I said, what about other bases? And I told you a rule, but we didn't talk about it much. Given y equals a to the x, where a is greater than 0, I should say a is not equal to 1. What is y prime? Now, I told you a rule for this, but we didn't derive it. We didn't see, like, where does the rule come from? And the reason we didn't derive it is because technically we need the chain rule in order to derive this rule. So let's work on this. Y equals a to the x. I'm going to do a little trick here. A lot of times in math, when we want to prove something or derive something, there's some clever trick that someone comes up with that seems a little odd at first. I'm going to say a is equal to e to the ln a. That's the weird little trick for this proof. So what's weird about this? I mean, it's true, right? It is true that a is equal to e to the ln a because the e and the ln cancel each other out. So that part's not weird. It is true. What's weird is a lot of people wouldn't think to come up with this first step. Like, why are we doing this? Okay, so I agree that it's true, but why are we doing it? The answer is because it's going to help us. I'm going to take both sides and raise them to the power of x. So left-hand side to the x and right-hand side to the x. We're going to wind up using this to come up with a derivative rule for a to the x. I'm going to leave the left-hand side the way it is, and I'm going to rearrange the right-hand side a little bit. There's a property of exponents that says instead of raising it to the ln a and then raising it to the x, I could raise it to the ln a times x. So what we've just found is that y prime, which would be d dx of a to the x, is equal to d dx of this. All right, do you agree with that so far? What's useful about this weird form with the e to the ln a, what's useful about this is that we can differentiate this using the chain rule. It's a function inside a function. So you know how I said sometimes the inner function is something that appears up in an exponent? That's what's happening here. We said the inner function could be in parentheses, under a square root, in an exponent. So I'm going to say that the entire exponent here, the ln a times x, that's my inner function. My outer function is e raised to a power, so e to the u. In this context, when we take f prime, we're taking the derivative where u is the variable, so the derivative of e to the u is e to the u. Just equals itself. What's the derivative of ln a times x? Well, in this entire discussion we're having, we're kind of assuming that a is a constant, right? It's greater than 0, it's not equal to 1. You know, x is the variable, a is a constant. So if a is a constant, then ln a is also a constant. It's just some number. So we have a number times x. When you take the derivative of a number times x, you just get that number. What I just did in that step, it's sort of like if I asked you, what's the derivative of 7x? You would say it's 7. If I said, what's the derivative of 3x? You'd say it's 3. If I say, what's the derivative of ln ax? It's ln a. All right, moving on, let's apply the chain rule formula, right? Y prime, we have all 4 puzzle pieces, but let's actually put it into the chain rule formula and see what we get. So f prime is e to the something. We need e to the g of x, so e raised to the ln a x, and then times g prime. Take a look at this. E to the ln a x. Earlier, we said e to the ln a x is equal to a to the x. So this could be rewritten as a to the x times ln a. And that means that the rule for the derivative of an exponential function is the derivative of a to the x equals a to the x times ln a. And this is the rule that I told you in that previous lesson. But now maybe you can see where it came from. It came from this little trick at the beginning and then using the chain rule. Cool. So that's, you know, I would say the chain rule is a very practical thing. Like, we can use it to solve problems, but it's also useful that the chain rule helped us derive this rule. All right, so the rest of this section is basically going to be just more problems, more example problems of applying the chain rule. And I think what we'll do is I'll do some myself and I'll ask you to try some on your own. And we're going to see some different situations that come up. Some of these problems we might need to talk about a little bit. But I'm going to start it off with a problem for you to try. So I'll write it and then you can pause the video and try to differentiate. So find the derivative of this. Y equals 5 raised to the 1 minus x squared. All right, so hopefully you paused the video and tried that. I think what we should do is we should set up f of u, g of x. I guess maybe the first thing to do before we even set that up is take a look at the problem and ask yourself, you know, is this a chain rule problem? Can I do this with the product rule, quotient rule, some other rule? Well, I think we know how to do the derivative of 5 raised to the x. That, you know, if it was just 5 to the x, we would use this. But the problem is it's 5 to something else. This is a composite function. This is a function inside a function. So chain rule is the correct rule here. The inner function is the part that's in the exponent, 1 minus x squared. And that means the outer function is 5 to the u. Remember, you can check. You can check to make sure that you've set it up correctly. Y equals f of g of x. That's how you know that you set it up correctly. I'm going to put a little check mark next to that. the original y in the problem is equal to this f of g of x. Okay, that's not any derivatives. That's just checking that we set these up right. All right, so what's the derivative of 5 to the u? That's the rule that we just set up above. That's 5 to the u ln 5, where ln 5 is just some kind of number, some kind of decimal, but we leave it as ln 5. The derivative here is minus 2x. So the chain rule formula says f prime of g of x times g prime of x. So it's the derivative of f of g and then times the derivative of the inner function. So f prime is 5 to the u ln 5, but we need it to be 5 to the 1 minus x squared times ln 5 times g prime of x is negative 2x. Okay, that's what I got. Should we write this any differently? It looks a little weird to me the way we wrote it. I think we could probably find a nicer way to write this. Like the minus 2x, we want to make clear that this is not being subtracted from the other stuff. It's being multiplied by a negative number. And usually a constant like negative 2 would be out front. But for that matter, ln 5 is also a constant. So I'm going to rewrite this as negative 2 ln 5. And then maybe put that in parentheses. And then you could say like x times 5 to the 1 minus x squared. I don't know. There's a couple of different ways you could write this. But you should get something like that. Let's do another one. I just like to bring constants out front. That's the main thing there. This next one I will do. So don't worry about trying this because something a little bit different is going to happen. This is y equals sine of cosine of e to the x. Now, this is not a product, right? Because it's not sine times cosine. It's sine of cosine. It's really different if it's, times or of. We want sine of cosine of e to the x. So there's a function all the way on the inside, and then there's a function in the middle, and then there's a function all the way on the outside. So this problem is a little bit different for that reason. How about we say f of u equals something, g of x equals something, f prime, g prime. All right, so that's good. We're getting started. I think that we could look at sine and say sine is sort of the outermost function. So I'm going to say f of u is sine of u. And that means that the inner function is everything inside these parentheses. So everything inside these parentheses would be cosine of e to the x. Sometimes I find g first, sometimes I find f first, just whichever one seems easier to you. And for the derivatives, g prime and f prime, find whichever one you want first. Doesn't matter, because you're going to need to find both anyway. How about we find f prime first? That looks easier. Derivative of sine is cosine, so this is cosine u. So we got the easy one out of the way. What's the derivative of this? Cosine e to the x. That's a function inside a function, so we need to use the chain rule again. That's what I wanted to show you with this problem. It's the chain rule inside the chain rule. So in order to find g prime, we need to think like cosine is on the outside, e to the x on the inside. So what do we want to do here? Do we want to set up the 4 pieces again and use the formula? I think we do. We already have some stuff on our page that's called f of u, g of x, f prime, g prime. So are we going to do that again here? Well, you have 2 options. First of all, you could do that. You could say f of u, g of x, f prime of u, g prime of x. If you set it up this way, we're doing this with the understanding that we're doing the chain rule again. We're kind of one level deeper into the problem. So this f and this g are going to be based on this little problem we're trying to solve. So this f and g might be different from like this f and this g. And it's perfectly okay to do that. However, if it bothers you that we're reusing the same letters, you could just use different letters. Instead of calling this f, you could call it h. Instead of calling this G, you could call it K. And that's just a matter of personal preference. You know, if it bothers you that I'm reusing the same letters within the same problem, call it something else. Or you know what? How about this? Call this F2 and G2. F2 prime, G2 prime. So that's, I'm going to say that's up to you. I think from the way that we wrote this, I think it's clear what we're doing. I think what we're doing is clear. So I think that this is fine. I'm going to say that the inner function is e to the x and the outer function is cosine u. See what I mean? We're just working on this problem now. The derivative of e to the x is e to the x, and the derivative of cosine u is negative sine u. So, why were we doing this? We are trying to find g prime of x. So the chain rule formula, says to do f prime of g of x times g prime of x. And let's see what this gets us. F prime is negative sine of u, so negative sine of g times g prime, which is e to the x. All of that was to find this g prime equals this. We're not done with the whole problem. That's not the final answer, right? All we've done is we've found the 4 pieces that we need to apply the chain rule to y. So now we use the chain rule on y. Chain rule formula. See how I kind of did this whole problem just kind of in this area of the page? I think it made it clear what we were doing. And now we're kind of backing out to deal with the overall problem. So chain rule formula. F prime is this one, cosine of u. So we want cosine of something. Cosine of g of x was up here. This g needs to go in. So cosine e to the x times g prime of x. It's this g prime of x that we just found. So negative sine e to the x times e to the x. You probably know what I'm going to say is I'd like to rewrite this just slightly differently for the final answer. We did it though. We found all the pieces. It kind of bugs me to see times minus, because if you just look at this problem like as a quick glance, it might look like subtraction. So I think what's going to make it clearer is if we take the minus sign and move it out front. And that's the only thing I'm going to do to this one. I'm going to move the minus sign out front. See how that kind of makes it clearer that we're not doing subtraction. We just have a negative. All right, that's the answer. That is a big, weird-looking answer, but it was kind of a weird-looking function to begin with. I don't even know what that function would look like. Sine of cosine of e to the x. Weird function with a weird answer. All right, so this is the part where I tell you that this sort of thing can happen. You could have a problem where you have to use the chain rule more than once. Sometimes you might have to use it 3 times. Like, what if we were trying to find this g prime or this f prime and we had like we had to do the chain rule again. That could happen. And this is basically why it's called the chain rule. The idea is that a problem can branch off into multiple layers deep of using the chain rule. And they're all kind of chain, different links on the chain. I'll say that usually we'll just have the chain rule once or twice. Maybe 3 times might show up. But you should be ready for problems like this where you have to do it twice. All right, ready for another problem? I mean, it's pre-recorded video. I kind of say things like that, but remember, if you ever need to, you can always kind of pause, try to digest everything we've said so far. You could always rewind and review things. All right, here we go. We are going to try to differentiate, and I'm going to do this one for us also. I'll have one for you to do after this. But we're going to differentiate y equals e to the 2x sine x. First thing to do is to identify, is this a chain rule problem? I mean, it's in the chain rule section, so yeah, probably. But wait a second. Isn't this a product? E to the 2x times sine x? Couldn't I underline and say this is like my first piece and this is my second piece? So first, we're going to use the product rule. And I think within this problem, we're still going to need the chain rule, but we need to do the product rule first. Because first and foremost, this is a product. E to the 2x times sine x. So I'm going to do y prime is equal to, remember the product rule? First function times derivative of the second one plus sine. Second function times derivative of the first one. All right, take a look at this. We do need the chain rule, don't we? For this part right here. Let's move this over here and say we're going to do the chain rule for this. Because it's e to the 2x. Now, we know how to do the derivative of e to the x. But when it's e to the 2x, there's more going on. It's just a function inside a function. The 2x is the inner function. So chain rule for this piece, just for dx of e to the 2x. Let's set up f and g and f prime and g prime. So this is a problem that uses a combination of rules. It uses the product rule and the chain rule in the same problem. Maybe later, I don't know, we might have one that uses the quotient rule also. So sometimes multiple rules in one problem. Okay, I said already that the inner function is 2 to the x. That means the outer function is e to the u. The derivative of e to the u is e to the u, and the derivative of 2x is 2. So the chain rule formula for this, I'm going to write the formula each time we use it because I want us to get used to it. And I think I've said this before, but I think writing a formula every time you use it is a good way to memorize it. Okay, e raised to the 2x times 2. E to the 2x times 2. Is that what we were expecting? Oh, by the way, let's move the 2 out front. It's a constant. I like to move it out front. So all of this stuff off to the side, I'm going to kind of section this off. That was like a problem within the problem, right? It's not the finished answer. That's just what we needed for this piece. What do you think? Were you expecting this derivative to equal 2e to the 2x? You might have looked at this and you might have said, oh, well, the derivative of e to the x is itself, so maybe the derivative of this is itself. But it turns out that a 2 appears out front. Really, the 2 appeared to the right, and we moved it out front. Where did that 2 come from? That 2 came from, in the chain rule, I've been saying that you always wind up doing times the derivative of the inner function. So the more of these problems that you do, the more you might be able to start doing them in your head. For little things like this chain rule stuff that we did off to the side, you might be able to do it in your head. You might be able to say, I know it's going to be, well, the derivative of e to the u is e to the u. So it's basically going to be e to the 2x times the derivative of 2x. Anyway, that's why it's this, 2e to the 2x. So let's continue with the main part of the problem. We have e to the 2x cosine x plus, sine x times, let's put parentheses here, times 2e to the 2x. What do you think? Do you see any way that we could maybe rewrite this a little bit nicer? I think I see something. I see that both terms of this answer have e to the 2x, so I think I'm going to pull e to the 2x out. E to the 2x, e to the 2x, so that's going to leave me with a cosine x plus 2 sine x. That's a good looking answer. I like that. All right, ready to do some more? I'm going to give you a problem to try. I'm going to give you a problem to try, and it's going to be phrased a little bit differently. All of these problems that we've been doing lately have just been, here's a function, find the derivative. And of course, that's pretty common at this point in the course. Here's a function, find the derivative. But for this one, I'm going to ask you something else. So wait till I write the whole thing. Given y equals 2 raised to the x sine x, what is the slope of the tangent line at the point 0, 1? So I'd like you to pause the video and try this problem for a couple of minutes. All right, so we haven't done a slope of the tangent line problem in a while, but we've been doing derivative problems, and we know the derivative can give us the slope of the tangent line. By the way, the answer to this problem should just be a number, right? Because it says, what is the slope of a tangent line? So the answer is a number. Slope's always a number. Okay, let's, well, we look at this and we say, I know I'm going to need the derivative. So let's say f of u, g of x, f prime of u, g prime of x. I know we're going to need these pieces to use the chain rule. The inner function in this case would be the part that's up there in the parentheses. I'm sorry, in the exponent, I should say. Not parentheses. That means the outer function is 2 to the u. We have to do both of these little derivatives. Do whichever one you want first. I'm going to do this one, 2 to the u. The derivative of 2 to the u is 2 to the u ln 2. What's the derivative of this thing? This is a product rule. Product, first function, second function. So let's do, we've done product rule a lot of times, so I'm going to do this a little bit, a little simpler without writing so much. First function times derivative of the second one plus the second function times the derivative of the first one. It's okay to do that. You don't have to write as much now that we've done the product rule for a while. There's a times 1. We don't need to write times 1. Okay. What are we doing here? We're finding the derivative. Y prime is the chain rule formula, which we've written a bunch of times today. And let's put all this stuff together to get this. So f prime of g means we need 2 to the u ln 2, but instead of u, we're going to write this, x sine x. So 2 to the x sine x times ln 2 times this other stuff. G prime is this whole thing. I'll put parentheses around it to make sure that it's treated as one object where those two things stay together. So what is this? What does this represent? We found y prime. If this problem had just said to find the derivative, I mean, we found the derivative. This is y prime. So it tells us the slope of the tangent line at x, right? Let me move the page over so you can see that. This whole thing is y prime, so it tells us the slope of the tangent line at x. That's what the derivative tells us. What x value do we want? We want this, right? We were given the point. This is our point of interest. There's x, there's y. It turns out we don't even need y. We didn't even need 0, 1. The problem could have just said at the x value 0, because that's all we really need. We're going to use at x equals 0. We're going to put 0 into this. The slope is going to be equal to 2 to the 0 times sine 0 times ln 2 times 0 cosine 0 plus sine 0. I put 0 everywhere that an x appears. This should simplify to a number. You have to remember what sine 0 is and what cosine 0 is. All right. Sine of 0. Here, let's write some of these. Sine of 0, or maybe, yeah, we'll write it underneath. Sine of 0 is 0. Cosine of 0 is 1, right? So this thing here is 2 to the 0. 2 to the 0 is 1. It's 1. All right, so what have I got? I've got 1 times ln 2 times... It looks like there's a 1 here, but don't forget that there's a 0. There's a 0 in front of it. So this is going to be times 0 plus 0. It's ln 2 times 0. The answer is 0. There's just so many zeros that everything cancels away. For a second there, it looked like maybe it was going to be ln 2, but ln 2 times 0 is 0. So that's the answer. The slope of the tangent line to the curve at that particular point is 0. So you find the derivative, and then you plug in whatever x value it told you. All right, let's keep going. Let's see. So that one I just asked you to do, so I'm going to do this next one. So wait till I write this, and you know, I said I'm going to do this, so you don't have to you don't have to pause or anything, but here. There's going to be 2 parts. First of all, we're going to be told to find y prime, y double prime. Remember what this notation is? The first derivative, second derivative, third derivative, fourth derivative. And part B, what is this? Wow. Wow, so that is us taking the derivative 3,724 times. Wow, can we do that? All right, I'm going to do this one. So it's another type of problem that's a little bit different than just finding the derivative, but part A says find the derivative. So let's start out with part A, and let's start out with, is this even a chain rule problem? I guess there are two ways you could do this. I'm going to look at this and say that the negative x is like an inner function. So yes, I'm going to use the chain rule. The other way that I think you could do this is you could say e to the negative x is 1 over e to the x, and then you'd have to use the quotient rule, because you'd have 1 up top and e to the x on the bottom. So technically you could do this with the quotient rule. I'm going to use the chain rule. F of u equals e to the u. G of x is negative x. F prime of u equals e to the u. G prime of x equals negative 1. It's a little bit like when we had the e to the 2x in one of those previous problems. You know, just having a 2 up there, or just having a minus 1 up there, or just some number up there, it makes it like a chain rule problem. All right, so what do? Y prime equals the chain rule formula, which is going to be e to the negative x times negative 1, or negative e to the negative x. Maybe I'll put a box around that, because that's part of the answer to part A. We found y prime. Next, it wants us to find the second derivative. So we want the derivative of this. Do we need to do the chain rule all over again? What do you think? It's a composite function. Well, it's really the same function that we just differentiated, except it has a minus sign out front. So we're trying to find the derivative of this, but the minus sign can just be pulled out front. Do you see what I mean? It's the same problem we just did, but with a minus sign out front. So we're going to get the same answer we just got, but with a minus sign out front. Same answer I put a box around, but now with a minus sign out front. Well, now it's a double negative, so they cancel each other, and it becomes positive. And that's going to be my answer for the second derivative. How about the third derivative? Third derivative, let's continue this up here, I guess. Yeah, we'll continue this up here. We're still on part A, but the third derivative, it's the derivative of this. Do we know the derivative of this? Yeah, we just did it in part A. I mean, in the first part of part A. The derivative of e to the negative x is exactly what we did with this work right here. So it's this answer. It's negative e to the negative x. I don't have to rewrite the same work that we already did in this problem. What about the fourth derivative? We want to take the derivative of this. We already did that. We did that here. So we're going to get the same answer. We're going to get e to the negative x. So it appears that we have a pattern. We finished part A. We finished part A. And then we noticed a pattern, right? These are alternating. Negative e to the negative x, positive e to the negative x, negative e to the negative x, positive e to the negative x. And I can see what, the fifth derivative would be, and what the sixth derivative would be, and so on. It's going to alternate between these two answers forever. So if you ask me, what is the 3,724th derivative of this function? Well, we follow this pattern. negative, positive, negative, positive, negative, positive. And I notice that the first and third derivatives are the ones that had a negative in front. So the odd numbered derivatives had the negative answers. The second and fourth derivative have the positive e. So the even numbered derivatives have an answer of positive e to the negative x, because we recognized that pattern. Cool. So we just did it. That was a lot better than taking the derivative 3,724 times. We did it 4 times and recognized a pattern. That was good. Okay, I've got another problem for us. So I think I'm going to clear away this page. So if you need, you can pause to copy anything down. We're going to start a fresh sheet of paper for the last problem. All right, so this will be the last problem today, but it will be kind of a tough one, and I'm going to ask you to try it. So this is just a simple differentiate. It's not asking you for 3,000 times. It's not asking you for the slope of the tangent line or anything like that. It's just a differentiate problem. The thing that's going to make this problem a little bit harder is that you're going to need to use multiple rules, multiple derivative rules within the same problem. So f of x equals x e raised to the sine x. All of that is over 10 raised to the x. So I'd like you to pause and spend a few minutes on this one. Okay, so this is kind of a big problem. It has kind of a big answer. So hopefully what you figured out is that this problem actually uses the product rule, the quotient rule, and the chain rule all in one problem. Not necessarily in that order. I don't know. We'll see what order they're in. So we want to find f prime of x. I think that when I look at this problem, the first thing I see is that this is a quotient. There's something up top and something on the bottom. So I think the quotient rule should be used first. Maybe I'll label each rule when it comes up, but we're going to see all 3 of the big rules. So quotient rule says take the bottom function times the derivative of the top. Uh-oh, we're going to have to take the derivative of that. Minus the top function times the derivative of the bottom. All of that is over the bottom function squared. Okay. You know, the only hard part that's left is this. The derivative of this thing. That's the hard part, right? Let's work on this part. This, I want to kind of section this off and say we're going to do work for this part of the problem. This is a product. This is a product. There's an x times some other function. Okay, so let's use the product rule. My first function is x, so we do first function times derivative of the second one plus sign. second function times derivative of the first one. The derivative of x is just 1, so you don't even have to write that, but I'll write it anyway, times 1. So what do we do next? We still have to do this. This needs the chain rule. Wow. Okay. E to the sine x. So let's set up f of u, g of x, f prime of u, g prime of x, e to the sine x. So e to the u is the thing on the outside. Sine x is the thing on the inside. Luckily, the derivatives of each of these are not that bad. The derivative of sine x is cosine x. The derivative of e to the u is e to the u. The chain rule formula says this. So e to the sine x times cosine x. All right. So where are we at here? This is all this part of the problem. So this equals x times what we just found. So x e to the sine x times cosine x plus e to the sine x. All right, there was one other thing. So we found this part that I said was going to be the hardest part of the problem. We just found it. So we need to kind of piece everything back together. But before we do that, let's also figure out this derivative here, d dx of 10 to the x. So I'll take this and say that this equals, there was a derivative rule for a to the x. So 10 to the x ln 10 is going to be that thing. Okay, let's put this all together. We still have this big quotient. Don't lose any of the pieces of it. So now 10 to the x times what we just found, x e to the sine x times cosine x plus e to the sine x minus, what else was up here? Don't lose these pieces. X e to the sine x times 10 to the x ln 10. All of that was over 10 to the x squared. Now the good news is that technically we are finished differentiating. The only thing that remains is to see if this can be simplified in any way. But there's no more ddx's in this expression. All the derivatives have been evaluated. If we're lucky, maybe we'll find some things that cancel out or combine with each other. So let's see what happens. Up top, there's only two terms, right? There's like this big term here, and then there's a big minus sign. And then there's this other term. So two things up top. That's it. I have an idea. I see something we can cancel, right? We can cross something out here. Both terms up top have 10 to the x, and the denominator has 10 to the x squared. So we could cross out this 10 to the x and this 10 to the x and cross out the squared on the bottom. So let's see what we're left with once we do that. So then I have x e to the sine x cosine x plus e to the sine x minus x e to the sine x times ln 10 over 10 to the x, but it's not squared. Let's see if there's anything else we can do. I think I'm going to do one more thing. The one more thing that I want to do is I notice that every term in the numerator involves this e to the sine x, e to the sine x, e to the sine x. So I think it would be nice to pull that out front and have e to the sine x parentheses whatever else we have. So from the first term, we get x cosine x. From the middle term, we just get plus 1, because there was just 1 e to the sine x. And then we get minus x times ln 10. Well, it's x times ln 10. But I said that usually I prefer to write constants out front, so I'm going to do it as ln 10x instead of x ln 10. All of that is over 10 to the x. We are done. That is the answer. Wow. Okay, so that was a tough one. That was a tough one. And let's quickly move the page up and take a quick look at what we did. I'm just going to give you a second in case you're still writing down that last part. All right, so look at the function we were given. That is kind of a weird function. You know, I would look at this and say definitely quotient rule first. Quotient bar is cutting the problem in half. So yeah, we use the quotient rule. Good. As we were doing the quotient rule, we had to do this thing off to the side, which was a rule for the derivative of an exponential function. Fine, so we did that. And then this was the hard part here, where we had the derivative of this messy thing. And we broke that up and did that in the middle of the problem. And first and foremost, that was a product. So we applied the product rule. But then as we were doing the product rule, we got to something that was a composite function. E to the sine x needed the chain rule. So you could get problems like this that use multiple rules. Earlier today, we saw a problem that used the chain rule twice. And I think in a previous lesson, we saw a problem that used the product rule twice. So all different combinations of rules could get used depending on the problem. The chain rule was kind of the new part for us today. Luckily, the actual chain rule part of this problem wasn't so bad. E to the sine x had like relatively simple pieces. The hard part about this problem was probably using so many rules and then figuring out how to piece it all together and simplify it. But there's our answer at the bottom. So if you got this right, then you should feel really good about derivative rules. If you didn't get it right, don't feel bad. This was probably the hardest problem today, and there's going to be more practice problems where this came from. But I think we've done a good amount for this lesson. So I think we'll be wrapping things up here. All right, so we ended on kind of a hard problem, but I guess they can't all be easy ones, right? Some of them have to be hard. So the good news is that we're kind of finished with the big derivative rules. There's still going to be some small derivative rules that we still have to address. I would say that there's still some functions that we don't know how to differentiate yet. In particular, we haven't learned how to do derivatives of log functions, so we have to get to those eventually. But yeah, I would say that the big three rules, I think I've said this before, but the big three are the product rule, the quotient rule, and the chain rule. And you want to be really good at those three: product, quotient, and chain rule. So do some practice problems, work on homework, review problems and try to make sure you understand those three rules. And then going forward, a couple more rules for some smaller special cases. And we're going to start seeing some other things that we can do with the derivative besides just here's a function, find the derivative of it. Okay, so plenty more to come. All right, so I'll see you all next time. and take care.